Hey, everybody who's watching this recording. We are part of the Codex team, and we're going to explain how everything works, starting from the trusted setup ceremony, which we'll skip for now, but we'll edit it in post and include that in. We'll talk about the peer-to-peer network. We'll talk about the overall architecture. We'll talk about all of the processes that happen between all of the different entities in the network. We'll talk about altruistic mode, and we'll talk about persistence mode. And then we'll also sketch everything out, and then we'll hopefully come up with some Google slides at the end of this that make everything a lot more neater than just our freehand drawings. All right. So first, we begin with a file. I'm just going to draw the file that we're starting with. I'll make it yellow. So first we have a file. So we start with a file. Actually, let's start with the agents. Let's do that instead. Let's talk about everything. So we have the Codex node.
And we have a person.
We have a person. There you go. And so the person's running this Codex node on their local computer. And then beyond that, there's also other entities. There's a storage providing entity, right? So you have a Codex storage provider. I'll just put storage P for now. We also have validators.
I think you're drawing off screen right now, so you have to adjust the view.
Yeah, okay, it works. All right, Codex storage provider node validator. Okay, so we can do, let's blow this away.
That means we can just talk about Codex nodes and not make any distinction for validators or storage nodes, just Codex nodes.
I agree. Codex node. Peer-to-peer network starts with you connecting to one of the Bootstrap nodes that we run in our testnet cluster. So I'll say Bootstrap node. And then the Bootstrap node will give you other connections by sharing the SPRs. So what you're going to get, and SPR stands for Service Peer Records. So what you're going to get is, I'll represent the Codex node as this box here. You get a constellation of other nodes that might be in the network. And this is kind of what we were drawing as a cloud in some of our topologies. So we reference this as the Codex peer-to-peer network. Does that make sense?
Yeah, sounds about right.
Okay. And then...
So your Codex node talks to the Bootstrap node. And from the Bootstrap node, it learns about other nodes in the network. And so it joins the network.
Correct.
You want me to draw that like this?
Yeah, please. Just feel free to draw whatever.
Join, I can spell. Join network. There.
It's very dark mode for Miro.
Okay, so you run a Codex node. Your Codex node talks to one of the many Bootstrap nodes. And from the Bootstrap nodes, you learn the addresses of other nodes so that you can join the network. And then from nodes in the network, you can learn about more nodes in the network. And then if some of them drop or lose connection, you still have plenty of friends to talk to.
Do we want to talk about, there are 2 ports that are important to forward. So we have 8070.
They are configurable.
Yep. And 8090, which is
discovered. And it would probably be good to add that this
UDP
is a TCP port, and that is a UDP port. Those should be exposed to the internet so that other people can call you.
If you are unable to connect to the Bootstrap node, you can also do a direct peer connection.
Here is you. Here's your node. Let's say there's someone else with another node, and you want to exchange a file, and we can do that, right? Because that is a good example of just the peer-to-peer network.
We can draw that, I guess.
Let's draw the use case first. So, because then we know what we're talking about. So here's you, and you want to share a file because we're doing peer-to-peer file exchange for now, right? Let's say here is a Codex node of your friend, and they are also connected to the network. Here's your friend, Bren. And friend wants to receive the file, right? So, wants file. Then we can talk about the steps to get us there. So what happens? What's the first thing you do? is you upload your file to your Codex node, right? And we can draw that in several steps if you want. So here's you. You want to share a file. You have a Codex node running. Here's your friend. He wants a file and he has a Codex node running. So the first thing you would do is you upload your file to your Codex node. And we can draw that in several steps if you want.
Sure.
You want to take a stab at it?
Yep. So I'll do, follow me, I'm going to the left. So I'm going to say, here's your file. And what you do is you upload that to your local Codex node. And then what that spits out is it spits out a hash that's represented. It's called a CID, content identifier. And what that does is that allows you to share your, like where the data object is located with your friend. And if you share the CID, then they're able to, on their Codex node on their end, they're able to plug this in there, and then they're able to download this file that you uploaded into your Codex node to their Codex node. So this is how like file upload or file sharing, file upload and download. How file upload and download works.
Did you want to go into the blocks and the manifest and the tree and all that?
Yeah, I do. So like that's the high level how it works. So then I'll sketch this out. So what is really happening when we draw this arrow here? There's something there's something happening that is we abstract away. So your file, which is represented by this data set here, gets chunked into 64 kilobyte chunks, and then we take the Merkle root of this. So we take the root of the Merkle tree plus the tree root CID, which this also has its own CID, right? And all of these also have their own CIDs. And then we create what is called the basic manifest, which has a lot of data that is either, so I'll kind of draw it like this. So this is how a CID exists. So the basic manifest CID contains the tree root CID, which is the root of the Merkle tree, the data set size in bytes, the block size in bytes, which is what I mentioned before, currently hard-coded to 64 kilobytes, the multi-codec of the data set, which is an alphanumeric encoding, IPFS, which is what we kind of pulled from IPFS, and IPFS uses base 32 for CID v1. So I guess the other thing that we have noted is a manifest is a list of CIDs that are addressable as the CID itself, which we talked about. Technically, it's a Merkle tree that contains a bunch of CIDs, pointers to the content. A CID can point to either a manifest or a data chunk, but in the case of the CID pointing to the manifest exists as a tree of CIDs that points to the blocks that contain the data. And the basic manifest is available to the peer-to-peer network via the block exchange engine.
Do you want me to give it a try?
Sure.
Going through the flow.
Yeah, go for it.
Here's your file. And you stream it to your Codex node. So it's a stream. Then it gets cut into blocks of 64 kilobytes. We can hash the blocks, and that means each block gets its own unique identifier. So I'll represent that as a little point with the block. Here's a little point with each block has a little point. And each hash identifies the content of the block. So we call these content identifiers. Yeah?
Yep.
Now, after the whole file has been uploaded, you have a whole lot of these. You have like a whole bunch of little blocks here, and they each have a little identifier associated with them. They all have a little CID. Now, what you can do is a principle called a Merkle tree, where you hash them together in pairs of 2 to make the next level of hashes. So there'll be exactly half as many, sort of. And then you do that again. And then you do that again and again and again. And eventually you end up with a single hash on top. And we call that one the tree root. Now, the tree root implicitly identifies all the blocks that make up the tree. If any of the data and any of the blocks were to be different, then the tree root would be different, because the hash of the block would be different, and the next one would be different, and the next, and the next, and the next. So the tree root would be different. So this is almost enough to wrap up our treatment of the original file. What we do is we make a document. We make a document called a manifest. A manifest. And in the manifest, we put all the information we need about this data set. So obviously, we put the tree root in there, and then we put the size of the data set, and we put the block size, and a bunch of other properties. And that forms the basic manifest. But what you can do, because this is just data, and because it's just data, you can pour it into a block. So we turn this into a block, like all the other blocks, and then we hash it. And because we hash it, it has a CID, which is in principle no different from any of the other data blocks and any of the other CIDs, except that this has a little asterisk attached to it, by which we can tell that this CID belongs to a manifest, not just a data block. After that, these blocks all get stored on the local node. So all of these blocks and this block, they all get stored in a big box called the repo store. And the repo store is connected to something called the block exchange engine. I'm going to abbreviate that. Block exchange. These are tightly coupled. They are best friends. And what that means is anyone in the network can talk to your block exchange engine and ask it for a CID, and the block exchange engine will respond by sending that block of data. If we have it, send block.
And
It's a
this
little
is
bit more
happening
complicated than that, but
and this is happening on port 8070, right?
Yes, this is the TCP connection. Yeah. So practically, from the top, you have your file. It gets cut up into blocks. We hash the blocks. Then we hash the hashes, and we hash those hashes until we are done hashing. We have a single hash left. We make a tree out of all the hashes. Yeah, the tree root. Then we make a little document that describes the data set that we are just now uploading. It has the tree root, it has the size of the blocks, has some more stuff. We turn that data into a block. We treat it like any other block. We hash it again to get the CID of that block. And all of these blocks go into a big store where they can be accessed by anyone in the network as long as they have the CID. So after you have uploaded your file to your node and you want your friend to be able to download it, you give them this CID. Because once they have this CID, they can go to your block exchange engine and ask for the manifest block. The manifest block, they understand it has this information in it, and with this information, they'll be able to retrieve each block in the tree. When they have each block in the tree, they can glue all the data back together and they can recreate the original file. Make sense?
Yep. I like the way that you explained everything, but you also drew everything. I glossed over the Merkle tree. I just expected people that already knew how that works.
Yeah, well, I really appreciated people explaining the basics to me when I first encountered this. And it doesn't really take that much more effort to just sort of explain, like you hash hashes, and you hash hashes until you've hashed so many hashes that there's just one left.
Yeah.
But you see, if you go through the flow like this, your data ends up in this bucket, and from here it can be accessed by people. This is what happens when you upload a file to Codex.
I like your explanation a lot better. All right.
You want to do the next one?
Like for instance, we should probably talk about the API, just how they would make the request for CIDs.
Yeah, that's a good idea.
So like in terms of requesting data, right?
So to Store? No, not just. Let's not say store.
You can do a GET request through the default port 8080 to the local REST API for Codex, and then you can do a GET request for the manifest, the manifests that are the manifest CIDs that are stored locally on your node, and you can actually do a post request to upload the file. That's what Ben was talking about earlier in terms of pushing the data into your Codex node locally. And then when you're sharing it, it's basically just a GET request from the other person's Codex node to your node.
It's always better to reference the API.codex.storage. But currently, to upload a file, you post it to /data of your Codex node, and to get it, to download it, it is a get to /data
That'll help you. There you go.
/CID, that you put your CID here, /network, /stream, I think. /tree. I'm running out of space. Okay, there. I'm running out of space only on my screen.
There you go.
Yeah, that looks a lot better. Yeah, so what we can do is, now that you have your CID of your file, how do you request storage for it? You want to do that? You want to do, Jesse, you want to draw the flow from you have your CID to when you post the request on chain?
Sure. Okay. So when you're trying to pay to persist your file that you uploaded, you go through the setup, and then let me whip out my pen and the tablet. All right, so I will draw over here. I'll make a line here. I'll say this is persistence mode.
Okay, I'm driving the camera.
All right. So in persistence mode, we have that concept of the same file that you uploaded to your Codex node, and now we want to pay some money. So we put some collateral in in the form of potentially the CDX token. What's happening within the Codex node is it goes through an initial process of erasure coding the data. And let me see if I can flip to this. Okay, so we described it. So persistence mode begins when the user is requesting storage to be contractually provided for their basic manifest. Various prospective storage provider nodes who are looking at various different storage contracts that exist as smart contract offers can bid on any offers that they can satisfy in terms of price, duration, volume, otherwise like known as your storage capacity, collateral requirements, and then nines of durability, which will likely be a network constant in our case.
Yeah.
And then this creates the protected manifest. This protected manifest is the kind of erasure coded version of the basic manifest, and I'll try and sketch out how that works.
I put a huge comment on that bit of the document because storage providers can bid on the contract gives you the wrong impression, because there are no bids and there's no selecting of storage providers, right?
There is no selection of storage providers from the user standpoint. There's just like if the storage provider, isn't there a threshold of matching, automatic matching, or else it just doesn't work, right?
So the storage providers decide for themselves if the contract is interesting to them. And if it is, it will try to get a reservation on one of the slots.
But what do they actually see? Like, what does a storage provider see from the marketplace smart contracts? They just see the storage requests, right?
Yes.
And then the storage requests in terms of how they configure their storage node, is there a threshold, like for instance, for price? Do they set a range of prices?
No. The provider sets a minimum price per byte per second that they want.
Okay.
And if the request pays more than that, then it will consider it. But it's one of the factors, right? Because another factor could be the duration of the contract. Right. You could say, I don't want to store anything longer than 3 months, but the contract is for 4 months, then you will not participate.
So it looks like the parameters that the storage provider will be able to see and care about are duration, like Ben just mentioned, price per byte per second, proof probability, nodes, tolerance, collateral per byte, and expiry. And I guess we should go through each of those, and I'll write that. So this is part of the storage request. I'll write here. I'll sketch it out. Storage request.
Well,
So we take the previous blocks that Ben mentioned, and I'll draw it like this. So then we generate parity blocks. So I'll kind of number them how they're numbered in this drawing that Ben did. So 1, 2, 3, and then the rest of them, right? 4, 5, 6, and then it kind of continues on. So the way that Ben sketched it out here is we're generating parity blocks per column. So we're taking groups of potentially, like, let's say groups of 3 blocks. So this would be your column, or so your row 1, row 2, and then row 3, and so on. And so when we're constructing the columns, so it'd be like 1 is in column 1, 2 is in column 2, 3 is in column 3, right? So this is, I'll call it column 1, column 2, column 3. And we go through this process, and then we generate the parity blocks column wise, and I'll shade these as blue. All right, so each of these, so these are the column wise generated parity blocks, and then we'll call these A, B, C, right, up until I, and then we flatten this along with the originally chunked blocks in the original data set, and we flatten everything. So we take these parity blocks. So we have this. So you have A, B, C, D, E, F, G, H, I, right? So you have sets of 3 again. This is 1, all right. And then this is this row, and this is this row. So this was this row, this is this row. And we flatten to linear data set to store. So the light blue is represented by the erasure coded parity blocks, and then
yeah.
the ones that are white are the original blocks that were chunked. All right, and we flattened to a linear data set to store in protected manifest tree, right? And then it looks like you kind of so you took this, right,
Yeah.
and we'll just similar to what you did over here.
Yeah. 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 Right
We're
here.
just going to take that data set, right, and I'll just represent it like this. There you go. So we're taking that data set above, and then we're doing that same thing in terms of getting a we're creating a Merkle tree out of this new data set that has the erasure coded parity data appended to it, and then this, in the same fashion that we created the original basic manifest, we're creating this protected manifest that same way. So everything is essentially, you have the hashes of each of these blocks, and you're hashing the hashes together, like Ben mentioned, in pairs until you get to the top, the root, and then you have the protected manifest. Protected manifest, which
Yeah,
is
which includes all the same information as a normal manifest,
yeah.
plus the erasure coding parameters.
Okay. So I say I'll just mention this. This double asterisk includes EC parameters. There you go. Guess that's it for the protected manifest, and then we have to go through and then do this one more time for the verifiable manifest. I guess we should talk about how the way that, like, the details surrounding how we create the additional parity data is actually dependent upon the expansion factor that we choose to use. So I'll just denote expansion factor here is equal to 1 plus the erasure coded in the, like, ECM. This is M represents the original blocks divided by, I'll put it in lowercase, or ECM divided by ECK. There you go. So for every ECK data blocks, you get EC. Oh, so M is parity data. Okay. So M is the parity data. So if we have, if we have an expansion factor of 2, right? We're basically creating for every original data block, we basically have a parity block. So we just doubled the data. So if the original data set is, let's say, 1 gigabyte, and we have an expansion factor of 2, then we're creating another gigabyte of parity data. And so you have 2 gigabytes in total of parity data, or of the flattened data that goes into the protected manifest. And then there's also this data segmentation and placement and data placement strategies to prevent edge cases around like data withholding attacks, as far as I remember. And this is like tied to reconstruction. Because if you have all of the parity data in any one single slot and you lose that slot, then you lose the ability to, well, actually, if you have the original, it's not the parity data that you need, it's the original data that you don't want to lose. So yeah, if you want to make sure that there's some sort of random dispersal process.
How it works is you're here at the erasure coding, like the columns, right?
Yeah.
And so this column of parity data only protects the first column of original data. And the second column only protects the second column of original data. So when we shuffle the blocks across the hosts, it's very important that the parity data for a column is in a different place than the original data of that column. If they were both on the same host and that host would fail, then part of the data set would be lost. So the placement strategies you're talking about are such that the parity and the original data is distributed in such a way that there are no single points of failure, that we minimize points of failure.
Do you want to go through the verifiable manifest process?
Yeah, do you want me to take that from here?
Yeah.
Okay, so if we have the protected manifest, it's part original data, part parity data. I'm going to treat it as just data for now. So I'm going to draw a big line here and talk about how to create the verifiable manifest. The purpose of the verifiable manifest is that it can be used to generate storage proofs. You cannot generate storage proofs with the basic or the protected manifest. You have to turn it into a verifiable manifest. And here's how that works roughly. So we have the original data plus the parity data. It's just a bunch of blocks like this. And we want to distribute it among a number of hosts. Let's say 3 hosts. So we're going to cut it into 3 pieces and we're going to distribute those blocks in a clever way such that we maximize the chances that if any of these are lost because a host fails, the other parts can be used to reconstruct it. So here's the placement strategies in here somewhere. Placement strategy. To be able to generate storage proofs, we use a zero-knowledge circuit. And I'm going to proceed with only one of these segments from now on. They call them slots. So this would be a slot. And I'm going to show only for one of them, but the same thing happens for all of them. So here's my slot. And the zero-knowledge circuit runs on Poseidon 2 hashes, which are faster at hashing in a circuit than a SHA. And so all of our normal Merkle tree hashing is not useful because these are all SHAs. We have to sort of re-encode this data so that we can generate a Merkle tree and hashes that are useful for the circuit. And also, the unit of sampling currently is a block. Here's a block. A single block is 64 kilobytes. But that is too big for the proving system. The proving system much prefers the smaller unit. I'm going to draw them like this. So this is a block, and this is a cell. And a cell is only 2 kilobytes. What that means is there are 32 cells in one block. So here I have a bunch of blocks. Each block, so if we zoom in on a block again, here's a block. It has all these cells. There are 32 cells in a block. That's very convenient because that's a power of 2 and we need a power of 2. And what we can do is we can Poseidon hash each cell so that each one has a hash. And then we hash them together to build a Merkle tree with a root of this block. So this is a block root hashed with Poseidon 2. Yeah, that's important because the slot has a lot of blocks. Or here are the blocks, and for each of those, we can generate a block root in Poseidon 2 by hashing all the cells into a mini Merkle tree, right? And then the important thing that Jesse mentioned just now is the total number of cells in this slot. The total number of cells has to be a power of 2.
Why? Why does it have to be a power of 2, Ben?
It has to be the power of 2 because the shape of the data that goes into the proving circuit is not dynamic. It has to have the same shape, the same structure of the data goes into the proving circuit every time, right? So it has to fit that structure. So we have to pad the data if this is not a power of 2. So let's say it's not a power of 2. The cells in the slot are not a power of 2. Then we add blocks, empty blocks, to the slot until the number of cells is a power of 2. So here we have some padded slots. These all have their Poseidon hashes there. Then we can build the Merkle tree on top of this.
And this is the slot root.
And this is the slot root. Slot root.
There's also a mention of like you're actually doing two CIDs for each block. You're doing a SHA, like you're still doing a SHA hash, is what this says, and you're also like
the block originally when we created the block and we put it in the repo store, it has its own CID, which contains a SHA hash, right? So at this point, we have two ways of addressing the same block. We have the SHA hash, as represented by the CID, and we have the Poseidon 2. But the Poseidon 2 hashes only exist in the context of the proving system. And since we're building the verifiable manifest so that we can run the proving system, we have to deal with them here. So this is how you generate the slot root for a bunch of blocks, like a slot set of blocks. So if we go back to the picture up here a little, remember I said we had three slots right here. So we have the 3 slots here, and for each of these we have a slot root like this. Yeah. Now the last thing we need to do when it comes to hashing is the slot roots, the number of those also has to be a power of 2. So we add a sort of a well-known empty hash right there, like a default sort of well-known empty hash. Now this is a power of 2, and we do that so that we can once again build a damn tree like this, and we get a root on top that is the verification. Say that 10 times fast. Verification root. Right. Now, if you've been paying attention to what these hashes do, then you will understand that the verification root encompasses the entire data set, including the erasure coded data. If any of the data were to be changed or any of the parity data was changed, then this block, the cell trees would be different. So the block roots would be different. So the slot roots would be different. So the verification root would be different. So this verification root is very, very powerful. It identifies the entire erasure-coded protected data set. And the nice thing it does is it does it in such a way, this is Poseidon 2, once again, which is very useful for proving circuits. So when we go talk about how the proving circuit works, so when we set up the I'm just going to call it very manifest. Manifest has everything that the protected manifest had, plus it contains the verification root, this thing, and it contains the slot roots. Yeah, that's very important because that means it contains the top of this tree here, which is necessary because when you are a host, you are storing just one of these slots, which means you could conceivably reproduce the root of your own slot, but you could not reproduce all the slot roots unless you download the entire data set, which you're not paid to do. You're paid to have only the slot. So you need those other roots to generate the proofs. You need those other roots to generate the proofs, and you don't need to download all the other slots to get them. So they have to be in the verifiable manifest. The verifiable manifest then does the same trick that all the other manifests do. It turns itself into a block, a normal block, with a normal hash, just a normal CID, right? And this CID, which then by which you can retrieve the verifiable manifest, this becomes the content field used in the storage request. Storage request. Yeah.
Oh,
So the storage request
I,
goes on chain. It
yeah.
contains this CID. With that CID, you can retrieve the verifiable manifest. With the verifiable manifest, you can retrieve the slot that you are going to be storing for the duration of the contract. And it contains all the hashing information that you need to be able to generate proofs for it. Make sense?
Yeah, that's the right level of detail. We don't need to go any deeper than that.
Let's not. Okay. Yeah, I think this story is basically finished. The one about the creation of the storage requests.
Okay.
I mean, the rest is relatively simple. There are a few other fields in the storage request other than the content,
Yeah.
but those are the parameters that you mentioned earlier, like the duration and the price and the
Yep.
collateral and the
Yep.
durability parameters.
Okay, so you want to switch gears, let Guru present the developer like practical usage of Codex. All right, let's do that then.
Yeah, let's do that.
Okay, Guru, it's your turn. You take over.
So basically, this is a demonstration of a file sharing app that uses Codex for storage and Vaku for communications. But before we go there, for someone who wishes to build on top of the real Ethereum stack, which was proposed back in the Ethereum white paper, uh, this is how it used to look like on the white paper. I think this is a great image that can help developers understand how a truly decentralized application could be architectured, based on the Ethereum white paper. Oops, just want to open it in a new tab.
You're trying to show the holy
Yeah,
trinity where Swarm is taking care of storage.
exactly. Like I just want to make sure that people understand what is the difference between Swarm and Whisper. Because when we look at the Ethereum trilogy, Ethereum was meant just for the consensus layer. Swarm was meant for the storage layer, where it's basically Codex right now. So it's a decentralized storage network, which is content address storage. Every file on the DSN has its own unique content identifier. And there's also a generalized communication layer. So a lot of people misinterpret the generalized communication layer to also be the storage layer. For example, I've seen projects use Swaku to send file sizes of 2 GB or 1 GB, and that's how they look at Waku initially when we say them it's communications. But ideally, the way people should look at Waku, or at least developers should look at Waku and a Codex, is that Codex is Codex has the potential to handle bigger files, and Vaku is just something that can handle metadata of these files. So the maximum file size or the maximum object size of a Vaku object that is being communicated can just be 1 MB. And this is where something like Codex can be complementary to Vaku by letting people upload X amount of data, X size of data into uh, Codex, and then communicating the content address using Vaku. So that's exactly how the Ethereum white paper looked at these three complementing technologies. But over the years, people have just fancied blockchain more than the other two technologies for some reason. Uh, but yeah, this is how I personally would envision a decentralized application to be uh, on scale. So yeah, going ahead, we will be looking at a demonstration of this file sharing app, which uses Vaku for communicating the metadata between people who are in the same room, and will be using Codex for uploading the data into a DSN and then getting the CID, and then we use Waku for communicating. And I can also sketch this out kind of easily. So if you have a data, let's say the file name is carrot.png, and you want to upload this into Codex, and this gives you with a CID. So this is the unique content identifier that was discussed earlier in the theoretical part of this recording. And yeah, this is being communicated to the content topic in Waku, and there can be multiple people uh, who kind of publish and subscribe. That's how we call communications with Waku. There can be a peer which publishes a particular object into a content topic, and there can be multiple peers listening to the content topic. So let's say there is Bob over here who has carrot.png, and Bob basically uploads it into Codex, gets the CID, and the CID is being published into the content topic. And there can be multiple people uh, like like Ben and Alice and Jesse. So yeah, multiple peers who subscribe to the particular content topic and listen to the incoming messages. So looking at the protocols for publishing the message into the content topic, we use something called light push, which is basically a way to publish messages from a light client into the content topic. And there can be multiple listeners who listen to the content topic. We can use filter or store. So in this case, let us assume Ben is using filter and Alice is using store. So the difference between filter and store over here is filter is more for message ephemeral conversations or communications where there's no storage involved or no caching involved. And for Alice, this is going to be store where there's a caching layer involved. So if Bob sends a message a minute earlier, and if Alice is not subscribed to the content topic at that point, they can simply query a store node to get back the message. So another problem that we've seen with developers who wish to build on top of Waku is that they misinterpret store to be a permanent storage or a storage solution, but store is just a caching solution. And I really wish store was called cache so that people don't really misinterpret it this way. Yeah, but that's how the whole architecture looks like. The problem actually happens when you don't have smaller data. For example, if you have a data set, let's say 10 GB dot zip, imagine sending it on Waku directly without using Codex over here. Imagine this goes from here to here. That is exactly where Waku struggles in terms of larger data, and that's exactly where Codex can fill the gap by making it scalable for bigger data sizes. So I hope I was deep enough for making you understand the concept. But yeah, that's exactly what we're going to do now. We have XYZ123 as the room ID, and if Jesse and Ben can join the same room ID right now and listen to the files in the received files, I can try sending something.
You have a link for me?
And also, we have some ongoing issues with some browsers. For example, Brave browser does not identify Codex if you have your Brave shields on. So make sure to disable this if you are having it active. So in my end, I have the Codex connection active. I use the Codex installer to run the Codex node, and then yeah, I can see it active over here. But let me try uploading something to see if Jesse can receive it. Yeah, I just uploaded a picture. So we can see that the CID was generated successfully for the picture, and it has also sent the file metadata to the content topic, and also received it just to make sure that the message was sent.
That's weird. So now I have a green check for the Codex connection in the Codex app, but when I put the same Node API into the settings of your file sharing app,
Mhm.
it's coming up as Codex Node is not running in the API endpoint. Let me look at the network. Let me look at console, I guess. So I'm getting WebSocket connection failure.
Yeah, that's common with Waku. So that's just proof of trying to communicate with the Waku nodes.
Okay. Now I have a get request to the Codex API endpoint connection error connection refused. I didn't have this problem yesterday. I'm not really sure what's going on, and the Brave shields are disabled for me.
Oh, is it a remote API or the one that's running inside your machine?
It's the remote one, but that's what I used yesterday, and it worked just fine. I'm using WireGuard to the VPS instance that's running Codex on DAP node. That's what I used yesterday, and it worked just fine.
It's weird.
Also, again, the Codex app is working. So we can try the Codex app real quick, and then just fire files back and forth, and then we can try your app again. So let me upload something real quick. All right, upload successful. I'll give you a CID in the.
Oh, I don't actually have port forwarding set up right now, but I can try retrieving it again.
So it doesn't
Oh,
explain the
it
problem.
it does work. It does work. It actually worked today,
Oh,
but it did not work yesterday.
okay.
Yeah,
Interesting.
I think this is yeah, I'm not really sure what's happening with downloading part without port forward.
Yeah. So your Cipher share file sharing website is not it's not taking my Codex API endpoint.
Yeah,
Accidentally
I
moved
think this has to do with something with a remote node because I haven't really tried a remote.
because it worked for me yesterday.
Oh,
Guys,
Yeah.
yes.
there's some kind of argument I need to pass to Codex to let it allow course stuff.
Yeah.
Can
There's a
someone
flag.
show me that argument?
It's
Uh,
actually in the Codex installer's code base. I can show you.
Oh, I found it. It's
Second argument in.
API course origin equals asterisk.
Yeah.
Yeah, I am passing that to my node.
can you guys pull this file for me, or did you already download it, Guru?
Oh, I actually got it downloaded.
Okay.
Full video.mp4, right?
Yeah.
Wait, I'm gonna download it.
And also, I've been seeing that the Codex app has been glitching for some time for me, like this. Can you see my screen? Like,
Yeah. I haven't done that many files yet that happens. Let me add more.
yeah, it starts flickering sometimes. I think it's because of the number of files. Yeah, probably because of the scroll attributes.
I'll upload a bunch of files and see if it happens.
Ooh, it's a video file. What? Oh, you.
I didn't do it. I didn't do it originally. Corey,
It's April 11, 10 days from April 1.
You just perpetuate the harm. I see how it is.
correct. Yes, you are correct.
Yeah. This core stuff is preventing both the Codex app and the file sharing app from talking to my node, which is really
Oh,
sucky.
oh, is this a Codex node that you're running without using the installer?
Of course, I'm running a Docker
Oh,
image.
yeah. So that's actually a cause issue. Yeah, you just need to pass in the argument, but because by default the argument is not passed.
I am passing the argument.
I had to pass it twice for some reason to get it to work.
Interesting. So you pass it inside the Docker container and then also outside of the Docker container, or any.
Uh,
Every Codex argument you can set also as an environment variable, and everything in the Docker container is set as an environment variable.
So what do you mean by you set it twice? Did you set it in the environment variable? Oh, you're not running a Docker container, Guru, are you?
no, I was actually, so when I was initially doing the node handler part in the installer, I had
Yeah.
this cost issue, and I had to fix that. I had to give the API cost attribute twice, like on the same attribute section, and then it worked.
Actually, I suspect what's going on there is if the argument list is too long, which it is because there's all these bootstrap nodes in there, at some point it will just start ignoring them. And so if it's late in the list,
Exactly,
it will
exactly.
just miss it.
Yeah. So if I put it on the second, it works, and if I put it on the last, it does not. Exactly. So I had
Yeah.
to do it twice on the bottom and top so that one of them would work.
Yeah. So for the upgrade to the installer, I'm gonna try switching it instead of having arguments. Codex also supports a config file where you can put all the arguments in a file, and I'm going to see if we can run it that way and save us this trouble. But
Yeah.
I'm a little surprised it doesn't work from the Docker image.
Other issue that I got to know from Vaslav about the Vaku reliability part is if you have two tabs on the same IP, that also reduces the Vaku reliability. So if I have two tabs open here to demonstrate this, this is probably not going to be working well, which is
Lovely.
weird.
Interesting.
Yeah.
All right. So Codex is working. You can pull files from me, but I can't. I still can't put the the API endpoint that I'm passing to the Codex app is showing as offline in your app. I don't know why.
Oh, I hope. Okay, it did work yesterday, right?
It did work yesterday.
I suspected a cause issue over here as well, because I'm not sure if the DApp node instance is using the installer or if it uses Docker natively. But if it uses Docker, the same image as of Docker, then I feel like that's a cause issue again.
But why would I have had no problem using it
Yes,
yesterday and now
yeah.
today I have a problem? That doesn't make sense. There's
Maybe you
literally a
had
request.
the. Can you check if you have the course extension active? Maybe you had it
No, no,
active.
no. I don't have the course extension at all in this browser.
Okay.
Yeah.
But maybe turning it on should solve this problem, because this seems to be a.
I could try. Let me
Yeah.
download course extension. The course unblock. Okay. Still offline. Save config. Yeah, still offline.
Yeah.
Yeah, here,
That.
I'll show you. I'll just share my screen so you can see. Maybe I'm just doing something dumb. There you go. Taking forever. There you go. Okay. So you see, like yeah. See my screen, Guru?
Mhm.
So like, I'm fine on everything, right? And then when I switch over and I use that same address, here, I'll swap out. I'll hard refresh. So all I'm doing is I'm just swapping out this right here.
Okay. And you have to press the save config in the bottom. You did,
Yeah, I did.
right?
I've done that. Yeah, it doesn't
Oh,
matter.
that's so weird.
I mean, this is what I was using to send you all that stuff. Yeah,
Uh,
it's working. It's fine.
Maybe if you can later, clone the repository and replace there's a one line where I given the default API endpoint. If you can just replace that, I think we will be able to confirm if this is
Okay.
an issue with the app.
Yeah, can you just link the repo and then I'll.
Oh, it's right over there, the GitHub icon near the
Oh,
settings.
okay.
Yeah, so over here you just need to replace it, and inside the hooks folder there's a use codex file. You just need to replace it over there.
All right. Let's see.
Here's a CID for you to download using the app.
Okay. What is the name of the file?
Oh, it doesn't include it?
The app codex app does not know the file names by itself.
It's just a GIF, and it's just an image.
Yeah, I got it. A man with the blonde hair, or not sure if it's a man or a woman. Oh, with a cooler.
It's a movie reference.